Today we will talk about a non-technical, primarily non-technical, but very important chapter in the design of cable-stayed bridges, which are aesthetics. I have broken this a little bit difficult to deal with theme into basically 10 concrete guidelines which we will discuss. The old Romans, as in many cases Romans and Greeks, considered these aesthetic problems already. A famous Roman architect, Marcus Vitruvius Pollio, stated in his 10 volumes on architecture that the main requirements for a structure very generally are firmitas, utilitas, and venustas. Now, we will deal here today with the venustas, the beauty. Aesthetic judgment, which is required for considering beauty, can be achieved by learning and by education. There are generally two directions in which aesthetics, here we talk about aesthetics in structures and bridges, are considered. The one, popular opinion, is summarized in the saying, form follows function. You will all have heard that. That means if a structure, if a bridge is designed right, it will look all right. Which on first view is not so bad, because it's certainly clear if a structure is designed wrongly, if the flow of forces is wrong, it will normally not look beautiful. But especially engineering structures, say truss bridges of the 19th century, have shown that correct design does not necessarily result in a beautiful structure. So it can only be one aspect. The other consideration, we all know, goes from more feeling in aesthetics, and there are again some sayings, de gestibus non est disputandum. You can't discuss taste, or beauty is in the eye of the beholder, which means it's completely different how one person sees something and the other person sees something. So this is a very individual point of view. However, it is a fact that, say, a majority of interested people will judge a given structure rather similarly, either saying, yes, it's good looking, I like it, or it's ugly. So there are, beyond completely individual feelings, there are some general judgments which are common to most people, at least those who are interested. So my personal answer to these at least dual considerations is in the way the German poet Schiller has stated it in a, let me say, formally very well-known treatise, I don't know whether it's still known today, on grace and dignity, über Anmut und Schönheit. And Schiller considers there the classical ideal of beauty as started with the old Greeks. And he comes to the conclusion that a beautiful, I say, structure has to fulfill rational requirements, form follows function, as well as more felt requirements. So I like to say he combines the two considerations on a higher level dialectically. This is, I think, the answer. It must be rational and it has to fulfill some requirements from feel. We will today deal with the rational requirements, and for that purpose I have developed or summarized 10 aesthetic guidelines which can be used to judge a structure. It's not a recipe for like a cooking recipe. Thou shalt apply these rules and then you will reach a beautiful structure. No way. This can't be done. But it can be helpful if you're sitting with a design or looking on another design to have a way to check various points whether they are fulfilled. And by constantly looking and judging structures, that is what I call learning aesthetics, by being aware what is beautiful and what is not and why. So these 10 guidelines from clear structural system to, I always say, above all, simplicity, we will now go through with examples. A clear structural system is a requirement so that even an uneducated in structural engineering person, when he looks onto a structure, feels there is a right flow of forces, or a layman also has a fine feeling if there is a wrong flow of forces. So a clear structural system, we start with a continuous girder, deeply haunched. This is for road and rail, and it's very clear how the loads are transferred by bending, and where the biggest bending moments are over the piers, there is the greatest depth, most material. An arch also gives a clear impression. Here we see this is a fixed arch between rock slopes, and that's where the force is transferred and a light roadway is hung from this load-bearing arch. A cable-stayed bridge shows a clear system. We have a light beam hung up by towers, and the connection is done by cables. This, by the way, is a second prize for the stonecutter we did. We didn't win, we were runner-up, but it still hurts. I think it's a beautiful bridge we designed there. Of course, for simplicity, a suspension bridge cannot be beaten. I mean, there we just have the towers have what I call the washing line type main cables hang over, and the hangers and the beam. For clarity of structural system, you can't beat it. Next rule, good proportions. Good proportions in all directions and within the members of a bridge. A typical example, a continuous three-span girder, in this case across the Rhine River, city of Cologne, and it shows the simple main rules for designing a haunched girder. The depth ratio above the piers and in the center should be close to 2 to 1. Very simple. And the second rule is the depth of the beam in the center and here should be the same. And you should run horizontally, as a tangent, horizontally with the underside parallel to the top into the end structure. And if you just follow these two rules, or three rules, 2 and 1, same depth and ending up parallel, you will nearly always design a good looking haunched girder. More involved haunched girder is this railway bridge with triangular piers. They look very well, I think, here with a 60-degree opening. 60-degree we have more often also in the inclination of diagonals. And however, it doesn't fit all the time. There needs to be a certain given height in order to make these 60-degree triangles look good. Here it was. In addition, there is a slide haunch in the, what I think 130 feet center. It's a Main River bridge for the high-speed railway line. So for this given situation, good proportions. An arch bridge also has simple base rules. Again, we have the rule 2 to 1. The ratio between the arch depth and the beam depth should be in the ratio of 2 to 1, or 1 and 2. It doesn't matter. You can put the bending stiffness either into the beam, like in this case here, the Tangermünde Elbe River Bridge has long, I don't know, maybe 600-700 meters approaches, which have a reasonable depth of 3 meters. So this depth of 3 meters of the approaches was taken through here, and that's a deep beam here. That means the bending stiffness of the tied arch consisting of beam, tie, beam, and arch. The bending stiffness lies in this case in the beam. So the arch only receives compression because the bending stiffness is given in the beam. So the arch can be very slender just for compression because we have a deep beam, and so we can come to a ratio of 2 to 1. It can be the other way around. You can have a heavy arch which also carries the bending stiffness, and a light roadway slab just hung to it. Then the arch has 2 and the beam has 1. But you must not use the same depth for the arch and the beam. 1 and 1, if you do that, it looks dull. You need a certain contrast inside the structure. So never make it 1 and 1. 2 and 1 this way or the other. And of course, color here can help. Color, dark color underlines the thickness of the beam, and the light highlights the slenderness of the arch. Next rule, good order. Very important. We must minimize the different directions of members in a structure to a minimum. Good order. This can be easily demonstrated in the arrangement of stay cables for cable-stayed bridges. The simplest way is the harp system, you remember, cables in parallel. And if we have only one center plane, well, there are no intersections, no nothing. The simplest arrangement of stay cables you can have. Also, when you have 2 cable planes in a harp arrangement, There are no visual intersections even when viewed skew from in an angle, you see. That is the big advantage of the harp arrangement. Now we come to the fan. You will remember from earlier lessons the fan arrangement is a little bit more economical. It needs a little bit less cable steel and less bending in the tower. So it's the usual system. And if we have, like here for Stonecutter in Hong Kong, just one central plane, well, there are no intersections visual of the cables, and it looks very orderly. However, when we then have two cable planes in fan, we have visual intersections between the stake cables when viewed from the side. This can, however, be mitigated firstly by using an A-tower, because then the cable planes at the top, and that's the case here for Yangpu, at the top are very close, intersections become less. And secondly, as Professor Leonhardt used to point out, if we then have many stake cables, like Yangpu, which was world record in 1994 with 602 meters, the many cables appear like a veil, ein Schleier. So in this veil, these intersections somehow disappear. 4 planes of stake cables we used for the Baytown Bridge we've mentioned before, because we needed 2 beams, independent beams for each section of travel. And so even here the towers are designed as simply as possible. I don't think you can design, except for a pin, which we didn't want. You can design simpler A-towers than we have done here, constant wall thickness and all that. So that gives the repetition, gives an impression of order. And the 4 planes of cables, of course, have the problem that here we have visual intersections that cannot be discussed away. But if the bridge is big enough and we have enough or many cables, we approach again this veil impression. Integration into the environment. Very important. If you have to design a bridge, you have to go to the site. If you don't do that, if you design especially a major bridge, but for every bridge, design just in your office, it's unprofessional. You have to go to the site and you have to find out what is the special feature of this particular location. And there normally is one. Maybe not easy to detect, and you can only find it if you're there. So go to the site before you start doing the design to find out what is the special characteristic of this particular site, so that the bridge can then be integrated into this particular environment. In this case, South Bridge Oberhabel in Berlin, the buildings in brownstone were existing when we had the task, together with the excellent architect, Professor Walter Nöbel, to design a bridge here. And as a result, we took up the piers on the side to support a special lighting system here, because it's mainly pedestrians. At the end, it looks as if the buildings and the bridge was designed together, mainly by the use of the same brownstones for these prominent pier extensions as used for the original buildings. So I think that's a good example how we can integrate, in this case by use of the same material, into the surroundings. Another example is the railway bridge Humboldt, across the Humboldthafen at the new main station, formerly Lehrter Bahnhof. Schleich and Gerkan Mark designed this railway station, and the bridge runs through and had to be concrete also because those are the areas where you walk on in the rail, in the station. So arch bridge looks very well, and so in this case the requirement that we normally use steel for compression, that we use concrete normally for compression and steel for bending was reversed, because we have here steel arches, but because this had to be concrete and one wanted to integrate this bridge, which runs into and through the station, with the steel glass station design, this was chosen. We did the detailed design on the steel part, and I can tell you it was a hell of a job. It was very difficult. But in the end, from the point of view of integration into the environment, it's a good example. Also, we have to respect the surroundings. Annapolis, as you may have heard, in Annapolis, it's a city in the northeast of the US. There is the famous Naval Academy from beginning of the United States, and it is actually here, the Naval Academy. So there was one of the few design competitions in the US to build. There was an existing one which had to be removed to build a new bridge there. And we were the only ones entering with a very simple bridge. We think, well designed, we will have some details later, but all the others had load-bearing structures above, being it arches, cable-stayed bridges, things like that. All not necessary. These spans were good enough, so by respecting the Naval Academy in the back and trying to design a subdued, visually low bridge with some detail considerations, and it's curved and all things like that. This leaves the Annapolis Naval Academy in its own right. And thanks, we won the competition on these considerations. There were some famous Myron Goldsmith was one of the judges, and quite a famous architect in the US, and some others, and they saw it exactly the way we had designed the bridge, so we felt understood. Another nice example is in Stuttgart. One of the very early pedestrian cable-stayed bridges around 1960 across the Schiller Street, and before that you went across the road on level, and there were two natural paths bifurcating into the park, and so this bifurcation was taken up in the bridge design. I mean, one could have done it straight and then, but no, the idea was we'd like to follow the environment, and I crossed over last week when I was in Stuttgart, and it just fits in a very nice way that's between parks, and so another way of fitting the environment. Choice of materials can have an important aesthetic effect. This is a little pedestrian bridge, timber. I designed very close to where I'm living now. I did that 10 years ago when I didn't know I was moving to Zeuthen in the south of Berlin at the Dahme. This is across the Dahme River there, beside the Autobahn. On one hand, it's light, compared 60-meter clear span, compared with other timber structures, it's very light. And the lightness is enhanced that we used steel for the end frames, quite consciously, because that's where the big forces come, all the wind transfers and so on, has to be taken here. And normally when that's also done in timber, it's really getting heavy and ugly. And so we said, no, timber is nice for the forces here in the span, but here at the end, where we have the heavy frame bending forces, with the appropriate material is steel. Why not? And we painted it differently, not in brown. We didn't try to hide it, but we used blue as a typical steel color, brown for timber. And so this is the appropriate use of materials, because now the end frame has roughly the same dimensions as the timber, and it doesn't stick out as rather heavy. So, using the materials as most appropriate. I come back to the Annapolis Bridge. Also, we have here a solid foundation, clad with natural stones, heavy. Then we have the uprising piers given a curved shape indicating the rising, and on top we have a lighter steel structure as the beam. So use of materials from the solid foundations, stone-clad, to the uprising curved concrete piers, to the rather light steel structure, a typical way from heavy to light by use of natural stones, concrete, steel. Typical arch bridge across the Elbe River at Pirna. We use, as is normally done, concrete as an arch. The bending stiffness is in the beam, so this takes only compression, can be thin. It's, of course, concrete as usual in compression. And in actual fact, this is a tied arch. The tie is in here. It's a turned around suspension bridge. So we also take the tension from the arch in the steel superstructure. It is actually a composite beam, but the steel takes the tension. So we have the use of concrete in compression and steel in bending and overall tension. This cable-stayed bridge, Helgeland, you've heard it more often, one of my favorites. We can argue that the main force in the beam and in the concrete is compression. There is some bending, yes, accepted, but the main force is compression. So what do we use for compression? Concrete. And of course, for the tension in the cables, we use steel cables. And we see here, you've heard it before, slenderness 1 in 350. These concrete compression members, if supported against buckling, can be made very slender and look well. Concrete not necessarily has to be heavy. Just have to use it the right way. Oops. Another proper use of materials, Rhine River Bridge, Flehe. We have here what I call hybrid cable-stayed bridge. We have the relatively light steel beam across the river, 320 meters something, and we have the heavy concrete approach, 60-meter spans where we anchor the stake cables, and of course the heavy concrete serves as a counterweight, as Kent ledge, as a counterweight for the steel main span. If this configuration is required, that we have here main span over water and a side span. This is normally a very effective use of materials. Coloring is an important factor, has to be used with care, but when done properly, it will enhance the view, the appearance of a bridge. Very white, cable stayed bridge, Dee River in Wales. The only tower I'm aware of right now which is completely made of precast elements with special, I say white concrete, it's not painted, it's through, and white concrete for the beam and white colored cables. I have never done this because with time it will become dirty. And it looks beautiful at the morning when you open it, especially when the sun shines. But so what I have used, especially for stay cables, was what we in Hamburg used to call marine white or broken white or off-white or whitish. Not the real white, because it becomes dirty and you see it very early. But whitish, we'll see it, I prefer. But this is how do you say that? The whitest, I'm not sure, the most white bridge I know of, the whitest is probably better. We used in Texas yellow cables. I mean, that's a decision that normally the client reserves for himself, that everybody can judge the color. There don't need to be a bridge engineer. But we were quite happy to use a yellow color here. That's Texas. Strong sun, deep blue sky, and I think the yellow appears well there. Rhine Bridge flare. The locked coil ropes are painted, as you know. In this case, it was painted in a red. The picture had to be improved. The colors have changed a little bit, I see. But what we use is, in German, it's Männige. English word is red lead for that. So it's a red which is not clear, but more like brownstone in the direction. Männige red. That's what it is. The colors are not completely right, which can be very nice. I always think a bad example, Saint-Nazaire, where was main world record, 404 meters until Normandy, I take it, 80s. And a very good bridge across the mouth of the Loire in France. But due to some reasons, apparently the Air Safety Commission required to stripe the tower. The only I know of, otherwise we always have these hazard beacons on top, which flash and so on, that's good enough. By the way, it so happened yesterday, the Tour de France went over the Saint-Nazaire Bridge, and I happened to switch on the TV, and I just saw them going over the Saint-Nazaire Bridge. It still looks like this, so I can assure you the picture's old, but it still looks like this. Space above bridge is something which is not quite obvious what we mean with that. The point is that with most bridges, when we pass over them, say by car, we do not realize that we cross a bridge. Of course, if we have a tower and arch, we see it. But the normal bridges, we do not recognize, except sometimes long, high bridges, if we approach them in a curve, then we can see, there's a big bridge. It feels like that. Okay, now we cannot make artificial curves to help us to see the bridge, but we can try to indicate at the bridge ends with some appropriate structure that we are entering or leaving a bridge. And that's one consideration. I mentioned already the South Bridge early on as fitting the environment. In this case, I was quite involved. I know how the design developed. We had the piers underneath, and then we had the lamp posts and so on. And then there was special lighting, and I think the architect said, why not taking this up? Now, in effect, this type, naturally, of piers growing on the sides above the bridge, that makes us aware, we're crossing a bridge. So that was not the purpose, well, other reasons, but it was in our mind that it's good to indicate the bridge. Naturally, if we have a cable-stayed bridge, we have a structure above, and as a driver you will see it. A-towers, which have many advantages, as you have realized, I've told you different times, have another advantage, that they form something like a tent. And I feel if you go through this tent, you feel safe, and it gives you some good feeling, and you can recognize the cables. Otherwise, sometimes it's not possible. 2 examples. A negative example, which I normally have avoided. I've only given good examples, but this, I think, demonstrates it well. And if I criticize something, I prefer to do it with my own bridges or LAP bridges. Now, in the early 70s and 60s, the freeway Heilbronn-Nürnberg had to cross the Kocher Valley. And the slopes were considered to slide. So initially it was said, thou shalt not place piers in the slopes, because they creep. So that meant very long side spans, and Leonhard, that was very early on when I started in Stuttgart, designed this, would have been world record cable-stayed bridge, 650 meters. Okay, that time models were built. There was no computer visualization. Either you had an architect to paint it, or you made models. And we normally had excellent model builder. He did this model and photographed, and that's what you looked at, and it looks very nice. Center plane of cables looks very nice from a bird's eye view, as we call it in English. However, this is the same bridge from the user's view, from a car driver. And there you see what I personally consider there are more, distinct disadvantages of a central plane of cables. When you approach the bridge, you don't know what this is. You just see some sort of a pin and cable. You cannot quickly recognize what this is. And when you then pass it, the cables go, and you have no grasp of what type of bridge that is. That is a definite disadvantage of a central plane. In addition, you need a box for torsional stiffness and. So I personally have never designed a cable-stayed bridge with one central plane. I've always used 2, if possible, with an A-tower, because I think that is the best. One reason I show you here to recognize it. Now, very important, recognizable flow of forces in the overall bridge. As I mentioned before, also non-engineers have a fine feeling whether that's a plausible run of forces, or whether the forces are, as we can taken for a ride, spazieren geführt werden. One reasonable approach was a design we did in the US. The tower shape, rational flow of forces, we tie them here together, then we have to take the beam in between, and want one foundation again, so we have to take it back. There are deviating forces where the kink in the legs is, so we take those up with a tie, post-tangent, and we have here the tension members. So I think it's very simple, very straightforward. Flow of forces is apparent to virtually everybody who looks at it. We went then with the Baytown, I told you, one step further, where we said, okay, we need two towers because we need two beams. And in this case, we connect them here, and then we have, well, it's not advertisement for McDonald's, although people in the US always said that, it's not. It's a very rational approach for transverse wind by truss action to do it this way with very slender dimensions. So it's designed purely from a flow of forces. It took us some time to come up with this solution, but then once we had it, obvious, must do it, from the flow of forces. Here we've mentioned, you remember the original design had a central tower, but was too high for the flight requirement from the nearby Düsseldorf airport. So they said, the flight safety people, not higher than this. It's not our design, but I know how it developed. So what was done then? Cut off the tower here, but if we would have taken the cables then here, they would have become very flat. They would have been uneconomical, 23, 24 degrees, 1 and 5, I told you that. If you become, then it's you come to some sort of extra dose and all funny things. So if then we said, okay, we want this angle unchanged, but can go only so high, it's rather easy. We make a V in longitudinal direction to anchor the cables in its original inclination. And naturally we need a strong tie to connect the forces here. But I think it's rather obvious by looking onto, even not knowing why the hell did they cut that off or something like that. But the flow of forces, that we have a load here transferred up, tied together here and taken back, I think people can understand. Rama 8 bridge, Bangkok. Sort of a hybrid bridge, but the concrete part is reduced to a real Kent ledge Gegengewicht. To counterweight, a real Kent ledge is one big concrete block here and a steel beam here, and it's all taken down to this heavy weight. I think it's obvious by looking on the run of cables how that works. We can also, and should do in detail, show the run of forces. Do not hide the cable anchorage at the beam. We could have put a cover plate on here. We could have, that much money would have been there, but we did consciously not do it because we wanted to show the flow of forces. We have here these are the 3 backstay cables, but the same system anyway. So we have here the high tensile forces. They run through the beam. That's where the cables are anchored. From here, they are introduced into the beam and run. These stiffeners indicate, of course, the force introduction. And then they run through the beam, which is heavy here, into the anchorage to the hold down pier via this 1 foot 305 millimeter pin. So shown clear run of forces underlined with the inclined stiffeners through the box, into the anchorage, into the beam, into the hold down pier. Clear run of forces. Don't hide it. Show it. Lighting can enhance. However, one word of caution. If you see a certain bridge only lit by night, it normally looks bad during the day. That's my experience. That's only beside the point. The Chinese people have a special feel for colors. So this type of blue anchor lighting underneath and yellow on top is quite common. We wouldn't do that in Germany, we would have it more uniform, but the Chinese like to do it. It's Nanpu that's beside the forerunner to Yangpu in Shanghai. Important, since many years we are not using separate lights to outline, say, the towers and things like that, but we use flat lights. Uniform flat lights on the beam maybe and lighting the cables, and that's a good example here. Baytown Bridge has also flat lights at the beam which light the stay cables and the towers uniformly. Heinola Bridge during sunset, so we have the lit bridge, we have the sun is going down. We have here individual lights, which I just said we don't need anymore, we don't use. Yes, as long as the navigational authority doesn't require them. And here it was, they said you must have lights for the ships to show. But otherwise it's quite a nice symphony of colors. Finally, above all, simplicity. The most important item for a bridge. A bridge design is only complete if we cannot take away anything anymore. And the interesting experience is we always start with the complicated. And it takes us maybe a long time and a long effort to get it down to the obvious simple, where everybody says, yeah, well, that's clear, that's the way it has to be. But we never start with the simple. One always starts with the complicated and has to put effort in, conscious effort, to narrow it down to the pure form where nothing can be taken off. Example, Weitingen Bridge, I mentioned here, originally, I remember well, it was early in the 70s, there were regular two-legged piers through the valley to take transverse wind, but 120 meter high, freeway Stuttgart, Lake Constance, Bodensee. And then at the end, Leonhard came and said, no, we don't need that, we make simple piers. Okay. So you cannot beat this single pin pier for a 30-meter wide freeway cross-section. That is the absolute minimum. Can't do less. Tangermünde Bridge shows we want to keep good order. We want to keep the different inclinations or directions in space of the members to a minimum. Therefore, we did not use the usual bracing, which would have introduced many new directions, but used Vierendeel system, which means pipes in bending, a little bit less efficient than the bracing, but less different directions makes a more orderly impression and is the absolute minimum of members we need, except there is another minimum where we don't use bracing at all. As here, the harbor bridge in Riesa is not a big span and is not very high. And if we would have put a bracing up here, people in a way would, even if we had the 425 meters, it's too low. And so purely from the aesthetics, one said, no, we don't make a bracing there at all, but you probably have learned it how to do that. You stiffen the arch transversely against buckling, and so it works. Costs a little more material, but the absolute most simple arch you can have no bracing. Very simple cable-stayed bridge, simple slender beam, several forestay, concentrated backstays. I always use this picture because this has the railing during construction. The final railing, in my eyes, was too solid. It's 1.3 meters high, disturbs the simplicity, so I always show this with the minimum temporary railing, but then it's very simple. And this you can't beat for simplicity. Little pedestrian arch bridge near Stuttgart, which Professor Leonhard designed. We basically have one member, the arch, a very light reddish railing. So this is, remember that's the ideal we strive for with regard to simplicity. Okay, final remarks. Collaboration between architect and engineers. As much as the architect is in charge of buildings and the engineer helps him with the designing flow of forces, the same way the engineer is in charge of bridges, because a bridge is primarily a technical structure, and the architect advises him on aesthetic improvements. If we have a jury in a competition, there should be a majority of engineers. If not, there are quite a number of examples that designs are chosen, selected, which later will not be built because they are too expensive and all sorts of difficulties. That normally does not happen with a design which has been selected by engineers. In general, the understanding of many people, aesthetics cost money, is wrong. Technical and economic requirements are not contrary to good aesthetics. If one wants to put it very flatly, but those things sometimes remain in the head, it's a question of using the same amount of quantity, but distributing it differently, you could say. So that makes it rather easy. Aesthetics don't cost money. If, say, flow of forces is wrong, and therefore aesthetics are wrong, then it's expensive. That costs money if you design wrongly. And basically what it boils down to is beautiful bridges are not more expensive than ugly ones. They require, however, additional efforts of creativity. Thank you.